Welcome to 37th lecture of graph theory. In the last class, we were trying to prove a theorem of Arrows saying that given an integer k, positive integer k greater than or equal to 3, we can get graphs, there exist graphs with chromatic number greater than equal to k and girth greater than equal to k. There are no short cycles, at the same time chromatic number is high. So, as we explained in the last class, these two requirements are somewhat contradictory to each other, because when you say there are no short cycles, at least when you look from a single vertex and select a vertex and look around it, it look like a tree to some distance, and it may seem that you can color it with very small number of colors. So, it is a natural question to think whether we can have all the cycles greater than or equal to some number k, given number you can fix a number k, maybe 1000 or something like that, and then ask, can I also have the chromatic number high? Typically dense graphs are high chromatic number. So, it may look like there are small cycles in it. To begin with, one may see that one may feel that okay, how do you make a graph with high chromatic number? So, you will say that if there is a big clique in it, then you can have chromatic number high, because the chromatic number is always greater than or equal to the clique size, maximum clique size. But then if someone asks, suppose I want to make sure that there are no big cliques, in fact there are not even triangles, 3 cycles themselves are not there, triangles 3 cliques themselves are not there, then can we still have the chromatic number high? So, it happens that there are some constructions, you have seen it earlier, Mycelian construction, and some examples we have seen where how we can get such graphs. And after that, of course, it may look like it is the cycles, it is not just 3 cycles, maybe if I avoid 4 cycles also, 5 cycles also. So, some up to k minus 1 length cycles I avoid, make all cycles large, then is it possible that I can always color the graph with very few number of colors, like a constant number of colors or something like that. But it so happens that however large case, you can get a graph with the chromatic number also greater than k, you can always make it large, both of them together large. This is what we were trying to prove. So, our approach was to use the probabilistic method, as we discussed in the last class. So, it was not so straightforward, it is not so straightforward to use probabilistic method here, because our strategy for showing that the chromatic number of a graph is high is by showing that there are no large independent sets. So, for instance, if you want to show that the chromatic number of a graph is greater than or equal to k, we will show that there are no independent set in the random graph, or there exists a graph that we will say that there exists a graph that with the biggest independent set size less than or equal to n by k. So, that the chromatic number becomes n by k, that means k greater than or equal to k. To show that, the typical strategy is to pick up a random graph. So, from the G and P distribution, one picks up a graph, and then one assesses the probability that there exists a large independent set of cardinality greater than or equal to n by k in it, and then we show that the probability is very low, tends to 0 as n tends to infinity, it is very low, and less than, we need only less than half for our purpose. So, this is what. So, but then we have to fix the probability p correctly. the intention here is to fix the probability. You know, if you fix this probability high, like half or something like that, it would be easy to prove the statement. But then we want to keep it low. Why? Because if you put half or 1/4 or some constant, it is likely that the graph we draw is from the distribution is dense, right. The expected number of edges is half of n choose 2. So, therefore, it is likely to be dense, but here we cannot avoid cycles. So, if you want to avoid cycles, the probability of picking an edge has to be kept quite small, and if you work with it, you will see that the probability has to be quite small, about constant by n. So, we have to keep this probability so low, like a constant by n, but then it so happens that if you pick up this probability to be g and p, that p is to some constant by n, this will not happen. We cannot make sure that there are no independent set of cardinality at least n by k. So, this range of probability for one of the things happen with high probability does not match with or does not intersect with the range of probability for which the other requirement happens with high probability, or with some reasonable probability. So, that we can add the bad probabilities together and show that it is less than 1. That was our strategy, right. So, now here we need a little trick. Rather than directly attacking or getting the requirement, we would rather get a condition which is very close to the requirement of having no short cycles, and then we will make some corrections. That is our plan. So, for that, yesterday we proved, we assessed clearly what should be the probability, how small I can make the probability, so that I can make sure that there are no large independent sets. For instance, instead of asking for independent sets of n by k should not be there, we ask n by 2k should not be there. That is a little technicality, we will understand it later. So, we will rather ask for I want the probability that the randomly selected graph contains an independent set of cardinality greater than or equal to n by 2k should be quite small. So, if you take any probability value greater than or equal to 6k log n by n, then we can easily show that as n tends to infinity, this probability that we do not like, right, this event, probability of this bad event will tend to 0, this will become 0, right. So, in other words, if you take n large enough, we can make the probability of alpha being greater than or equal to n by k to be less than, say, half, right. That is what we will need later. So, this is the key point. The probability that if we keep the probability high, this will definitely be happening. That means, this probability will indeed tend to 0, but then there will not be any large independent sets. But we are exploring how small you can make it, that probability value. So, we see that 6k log n by n is the smallest we can come, right. So, with respect to these calculations so assuming that this is the kind of sophistication that we can go with the calculations involved. So, but unfortunately, if you fix this probability p equal to this, there are short cycles, there will be short cycles, the probability has to be even less to avoid short cycles. So, our technique is this, that is what we are going to prove this statement. The technique is this. So, what will we do? We fix the probability a little higher only, that means of course higher than this probability here, the 6k log n by n, but little higher. So, how we select this little higher is you have k, the k is given with the problem. We want to avoid cycles of length less than k and have chromatic number greater than k. So, what we do is we fix an epsilon in between 0 and 1 by k, and then we will fix the probability to be p equal to n raised to epsilon minus 1. So, that is our probability is taken to be in between 0 and 1 by epsilon to be some epsilon value to be less than in between this thing, and then our probability value p is equal to 1 by n raised to 1 minus epsilon. So, we can also write it as n raised to epsilon minus 1 because. So, this is the value. You know, one good thing about selecting this probability is this probability is bigger than the 6k log n by n value that we have found for the other event to happen. That means, there are no independent set of cardinality at least 2k by 2n by n by 2k, right. So, this is bigger. So, this will happen if you with high probability. So, with high probability there will not be any independent sets of cardinality 6k by n cardinality n by 2k, right, n by 2k. So, now we see what we achieve by this thing is as we have already discussed, if you fix this probability, it is already too high, we cannot avoid all short cycles, but we would rather make sure that the number of short cycles, if you take this probability, would be small enough. How small? We will show that the number of short cycles can be made less than n by 2 with high probability, less than equal to n by 2, n being the number of vertices. This is what we are going to do, right. So, how do we do this thing? So, let us look. So, we will define, like we are going to use the concept of expectation here. Therefore, we need a random variable. What is the random variable? Let x of g denote the number of short cycles of length at most k. So, length at most k means it can be 3, 4, 5, 6 up to k minus 1, okay, also let us say at most k. So, chi of g denote the number of short cycles in a randomly known graph g, right, g element of g and p. Now, we had done this exercise in the last class. How much would be the expectation? We had seen that if we are looking at the expectation of I length cycles, if you are looking at the expectation of I length cycle, that will be npi into npi by 2i into p raised to I. This is what we had seen. So, we can make a comfortable. So, we can write it, this npi can be written as ni. This is another notation for npi, ni by 2i into p raised to I, p being that the probability of the g and p, this is this p, okay, p raised to I, is not it. So, so because to remind how it was done, the expectation of x is calculated by observing that this random variable x can be seen as the sum of several indicator random variables, where each of these xi will correspond to an indicator random variable which says 1 or 0 depending on whether a possible cycle will occur or not. We had discussed it in the last class, we will not repeat it. So, this therefore, and because each of these expectations by linearity of expectation, because there are npi by 2i of them here, right, and then p raised to I was the probability of this being 1, therefore, the expectation of xi was p raised to I. So, when you sum up, you got this thing. This is what we did in the last class. So, I won't repeat it. So, now, but the only difference is here we have to consider all lengths from 3 to k. It is not just one possible length, we have to consider all the lengths up to k, that means 3, 4 up to k. So, that is why we are summing up again, because as we can see we have all kinds of So, we can see that it is the expectation for the number of I length cycles, I equal to 3, I equal to 4, I equal to k. So, k different random variables are defined, and then if you sum up those things you will get x. So, therefore, to get the expectation of this you can sum up the expectation of the separate random variables for each I, and then that is why we get this. And then when you sum up this thing, what will you get? Because this n choose I is actually can be upper bound by n raised to I, and this is p raised to I. 1 by 2 is taken out, and this I can be discarded because we are just taking the upper bound, right. So, it is at least 3 onwards. So, we can discard it. So, this is at most half of sigma I equal to 3 to k n raised to I into p raised to I, and this n raised to, there are how many terms here? So, because we are going from I equal to 3 to k, there are k minus 2 terms here, and each of this term is upper bound by the biggest such term, say namely n raised to k, p raised to k. Because you see this we can see that n raised to k, p raised to k will be greater than or equal to n raised to I, p raised to I for I less than equal to k less than equal to 3. Why is it so? So, is it possible that this somehow decreases in after at some point? So, for instance, I somehow think that as we increase I, this should grow. That will grow because this n p is equal to n into 1 by n raised to 1 minus epsilon is equal to n raised to epsilon is greater than 1. This is a quantity greater than 1 by assumption. So, therefore, so we are assuming n is large enough, so that this is greater than 1, and so this will grow. So, therefore, n raised to k, p raised to k is indeed the biggest term among the n raised to I, p raised to I, n raised to I into p raised to I. So, therefore, we can substitute it with that. Half of k minus 2 into n raised to k times p raised to k will be the upper bound for this. Now, we ask what is the probability that the random variable gets a value greater than or equal to n by 2. Here, so here is an inequality. So, this x is a random variable with all positive values, right, because this is the number of cycles, it can be 0, 1, 2, 3 up to like all positive, no negative values. So, we can use that Markov inequality. In the last class we had just discussed the Markov inequality. What was that? It was we told when this random variable is positive, then the probability of this being greater than or equal to a is less than or equal to expectation of x divided by a. We can use the expectation to get a upper bound for the probability that x is greater than or equal to a, which is it is a very easy inequality. So, last time we discussed the proof of that also. So, and then now we can use it here. A becomes n by 2, therefore, expectation of x by n by 2. What you do is you substitute for the expectation here, namely k minus 2 into n raised to k minus k divide by n, because n minus k by 2. This half will cancel with the half here, n by 2, and then p raised to k is here. So, that is k minus 2 into, you substitute for p is equal to n raised to 1 minus epsilon. So, we can calculate that. So, here so let us say k minus 2 into n raised to k minus 1 into p raised to k equal to k minus 2 into n raised to k minus 1 into p is essentially 1 by n raised to 1 minus epsilon when you multiply by this k into k minus epsilon. So, this n raised to k will cancel, there is a minus 1 here. So, this minus k epsilon goes up. So, that is k minus 2 into n raised to k epsilon minus 1. Now, this epsilon was less than 1 by k. So, therefore, this quantity is going to be less than 1. So, this is k minus 2 into some quantity which is n raised to some negative quantity, say 1 by n raised to something, right, some positive quantity. So, as n tends to infinity, definitely this will tend to 0, right. So, therefore, we assume that limiting value n tends to infinity, probability that x greater than or equal to n by 2 is 0. Now, which means that if n is large enough, you can get that this probability is less than or equal to half, strictly less than half. Similarly, the earlier probability, namely the probability of having an independent set of cardinality greater than n by 2 k also can also tend to 0 as n tends to infinity. So, as n if n is taken sufficiently large, you can make it less than half there also. So, without difficulty, we see that for sufficiently large n, the probability that there exists a independent set of cardinality, greater than or equal to n by 2 k can be made, the probability that this happens can be made less than half, and also the probability that our x being greater than or equal to n by 2 can be made less than half. So, when you sum up these probabilities, that is, we will get the probability that at least this or this one, either this event or even this event happens, one of them happens. So, that will be strictly less than 1, that probability. Therefore, there exists a probability, non-zero probability, that we get a graph, there exists a non-zero probability that our randomly drawn graph has at most n by 2 short cycles, and there are no independent set of size cardinality strictly greater than or equal to n by 2 k. So, that means chromatic say okay, n by 2 k, the independent set size is small. Now, what you do is we take this graph, there exists one, so we can pick up that graph. So, there exists a graph. So, we are not looking for an efficient algorithm, but there exists one, therefore, suppose we take it, we get it, and then we know that there are only n by 2 cycles. If you remove one vertex from each of these cycles, all the cycles will be broken, all the short cycles will be broken, there will not be any more short cycles, but the number of vertices in the graph will reduce now to n by 2, because we may remove n by 2 vertices in this process. You may remove one vertex from each of the at most n by 2 cycles. So, you may remove the maximum n by 2 vertices. So, you will have n by 2 vertices left. Now, because you remove vertices, you will not increase the independent set size, it is still less than or equal to n by 2 k. So, but the number of vertices have reduced. So, the chromatic number of this graph is greater than or equal to n by 2 by n by 2 k, which is greater than equal to k as we wanted. So, we got a graph without short cycles, or whichever short cycles were there in the graph we have destroyed by carefully removing one vertex each from each of them, because we could do this because the number of short cycles were only less than n by 2, that is why we could do that. And then because we did not have any large independent sets, even n by 2 k sized, so therefore, even if the number of vertices have reduced a little bit, chromatic number has still to be high, because you divide by this, then we get a lower bound for them. So, we got a graph with both the required properties. This is what the key thing to observe in the proof is that it is, even if we wanted two properties to happen, but then there was no probability range which would ensure that with high probability or with some probability both of them will happen, it was not possible to do by the calculations that we do. So, therefore, we allowed a little bit, that means we told okay, I am looking for graph without short cycle, but I will allow a few short cycles to happen as long as the number of short cycles are small, here at most n by 2, and that was possible in a range. We could find a probability range, both of this happens, independent set size are also not big and also the number of short cycles are small enough. And then we processed it, because the small errors in the kind of the property we were looking for, it is deviating it from in a small way. So, we corrected it by breaking all the short cycles, and then we still had the property of no big independent sets. The number of vertices have reduced a little bit, but still, because the independent set sizes were quite small, the chromatic number of the graph has to be still big. That was the argument. That is the argument. So, now we will consider. So, this is enough for introducing the probabilistic method. So, we first problem was about getting a lower bound for the Ramsey number. It was very straight application. We just wanted two properties. One was to avoid large independent sets, and the other was to avoid large cliques. So, we found the bad events, namely there exists an independent set. We found the other bad event, namely there exists a large clique, and then we found the probabilities of that, and then we added these probabilities together to get an upper bound for the probability that one of these bad events occur, and then because we could show that these probabilities together will be still less than 1, because each of them were less than half, we inferred that there exists a probability for the good event to happen. That means, none of the bad events occur, right. That was a very straightforward application. Now, this previous example was more tricky, because we could not make that happen directly. So, we rather changed the property that we were looking for a little bit, assuming that somehow planning that later we will correct for the change, right. That's a trick there. So, that was a tricky application of probabilistic method. Now, we will quickly look at some other aspects of random graphs, rather than proving some structural theorems. We will look at some how some results regarding random graphs themselves can be obtained, right, without. Here we proved the GNP model to prove some theorems which essentially has nothing to do with randomness. It was finally when this results did not have any randomness in it, but here we are going to say something very different. This is about the random graphs themselves, the probability distribution itself. Here let us look at what a graph property is. Let P be a graph property. When I say P, it is a class of graphs closed under isomorphism. That means, if a graph is there, all the graphs isomorphic to it are also there in the set. So, any usual property that we are considering, for instance, the property of being connected is you can see as the set of graphs which are connected, right. All graphs, if a graph is connected, all graphs which are isomorphic to it are also connected, right. So, therefore, that is what a graph property. We can say that a graph property is just a class of graphs closed under isomorphism. And now, you take any function p of n, if g element of p tends to 1 as n tends to infinity. For instance, here you just consider the g and p model, and then suppose your p is some p of n, some function, fix it, right. And then if it so happens that the probability that the randomly drawn graph has the property, desired property p, that tends to 1 as n tends to infinity, one large number of vertices, then we will say that this property is there for almost all graphs. So, g element of this property for almost all graphs, or almost surely g has this property, like that. and the equivalently the other terminology is also used, namely suppose the probability that G has this property when a graph is randomly taken from the G and P distribution probabilistic space. So, then you if this probability tends to 0 as n tends to infinity, we will say that almost no graph element of G element of G and P has property P, or almost surely G does not have that property, right. So, therefore, this is the common a common terminology that we use in this area of random graphs. Almost surely some property is there, almost surely it does not have the property, like that. Now, for every constant so we will consider an example, some easy example for this thing. So, to show though it is almost intuitively obvious, we will take a small example. For every constant P element of 0, you take fix a constant, and every graph H, almost every graph G and P contains an induced copy of H. How do we prove this? So, you can fix a H. So, H may have say cardinal k vertices in it. Now, n is taken large compared to k. Now, you can what you can do, this is the randomly drawn graph. What you do is you can think of it as several group of n by k vertices. There are n by k vertices here. You can even write this n by k vertices here, n by k vertices here. Oh, sorry, we will say k vertices here, k vertices here, k vertices here. So, these are disjoint. We partition the n vertices into several k groups. So, we get around n by k, we can get at least n by k disjoint such collections. Now, we say that what is the probability that this k vertices contains H, that means there exists in a graph here, this graph is isomorphic to H. That probability is, of course, you can match in all possible ways. So, there are we can map, there are the vertices of this 1 2 3 4 n, it can be mapped to this in say k factorial ways, right. So, and then for each of them you can see whether it is isomorphic or not, so all the cases. So, we can count whatever it is, you can see that the probability will not depend on n, whether this has appeared it or not. So, this some function r which only depends on the probability will be some r which only depends on k, it does not depend on r. So, the probability that this does not have an isomorphic copy of H will be at most 1 minus r. Now, what is the probability that this does not have, this also does not have, this also does not have, this also does not have, none of them has. So, these are all independent events, because this is what is happening here will not affect what is happening here, in the sense that the edges here are totally different from the edges here. So, we can multiply these probabilities. So, it will become n by k, right, this will be the probability, and as we can easily see, this probability will tend to 0 as n tends to infinity, right. If you take, because this r is a number which is less than 1 anyway, because it is a probability, that is. So, therefore, therefore, you can see that as n tends to infinity, the probability that H is not isomorphic to any subgraph of G will tend to 0, any subgraph of G will tend to 0. So, therefore, we can say that almost surely G, a randomly drawn graph G will have the property that a fixed graph H has occurred as a subgraph of G, right. So, contains H as a subgraph. This is just to illustrate that terminology, that almost surely some property occurs, almost surely some property does not occur, right, that is what. We just want the probability to tend to 0 as n tends to infinity. So, nothing more than that. And now see now there is this interesting concept of threshold functions that we want to introduce. So, some properties are such that there are certain threshold, that means if the probability we select p is a little above the threshold, and then almost surely the graph will have that property, and if the probability that we select for g and p is a little below that threshold, then almost surely the graph will not have that property, the graph will not have that property. So, so more formally we have written here. So, let us say t equal to t of n is a function of n, and t of n is not equal to 0 for any of n, and we say it is a threshold function for a graph property p if the following holds for all p equal to p of n and g element of g and p. So, what should happen? See, if p by t tends to 0. So, this is the way of formalizing when I say p is a little above t. So, when I can say that by saying that if p by t, the function p is such that p by t tends to 0 as n tends to infinity. This means it is not exactly just more than, but it is a little, as a function wise it is a little more than that. T is also a function of n, p is also a function of n. If n tends to infinity, this will tend to 0. Sorry. So, here if tends to 0, it means that this is smaller than this, is slightly smaller than this in some way. This is a formal way of telling if limiting value of n tends to infinity, if this happens, it means that p of n is slightly qualitatively, intuitively we can say slightly smaller than t of n. So, it is small below the threshold, right. If this happens, our property should not be there, right. So, that means g should not belong to this thing with high probability. The probability that g does not belong to this thing should be 1, or probability that g belongs to p should tend to 1, right, as n tends to infinity or tends to 0. This is what we want, right. So, that is what we are saying. On the other hand, if p by t tends to 1 as tends to infinity, that means p is above the threshold function, then we want the limiting value of g element of p to be 1 as n tends to infinity. The probability that g elements of p should element of p, that means g has that probability, sorry, g has that property should tend to 1 as n tends to infinity, then this is called a threshold function. So, this is interesting phenomena that occurs in the context of random graphs. It so happens that several properties have this feature, that means it has a threshold function. That means the change from almost all graphs not having that property to almost all graphs having that property is abrupt. So, it is not that it is a very specific value, but it is a you can capture it this way, like p by t tends to 0 as n tends, see that means p is above t, p by tends to below t, and p by t tends to 1 as n tends to infinity means it is above t, right. This way we get a threshold function for many of these interesting properties, for connectedness, for most of the properties that we study. So, especially there is a theorem that if the property is monotonic, then there will always be the threshold function. So, we will quickly see. So, because we do not have much time to spend on random graphs, maybe we can maximum spend 1 more hour. Therefore, we will quickly see one example, because we are interested now how to show some threshold functions for certain properties. So, what are the techniques? So, today our intention is to introduce one method to prove the threshold functions. So, therefore we will, this is called we will introduce this method, it is called second moment method. So, for instance, consider a graph property of the form g such that a random variable x of g is greater than or equal to 1, where x is greater than or equal to 0 is a random variable. So, see, when we say random variable on graphs, most of the time we consider positive integer values, non-negative integer valued random variables. For instance, in the case of connectedness, it can be the number of spanning trees. If it is a disconnected graph, there is the number of spanning trees is 0. If it is a connected graph, the number of spanning trees is greater than or equal to 1 more or more, it can be many more, but this 0 or not will decide whether it is connected or not, right. Similarly, we can have many other possibilities, right. So, you can define the random variable accordingly and make sure that the property that we are looking for is captured by whether the random variable is 0 or 1 or more, right. So, because I am saying if it is 1 or more, then the property is existing. If it is less than 1, that means 0, equal to 0, then the property is not existing. So, this way many properties can be captured. So, we will look at this kind of properties now. So, we told one example connectedness, similarly other examples can be cooked up, so can be seen. So, the question here is, because quickly looking, how will we prove that such a property has a threshold function? This is what can be an approach, what can be an approach. So, this is what this is where we use the second moment method. See, one easy observation is that you can use this expectation. Suppose if you can somehow show that the expectation of x, this random variable, will tend to 0 as n tends to infinity. If n becomes large, if the expectation tends to 0, then it definitely means that the almost all graphs have the property p, because the property p is captured, if the property almost, so I should say if the property p is captured when chi of g is random variable has value greater than 1, then we should say that almost no graphs, or the other way as we define, right, almost no graphs have property p. So, that is because of the Markov inequality, because the probability that x greater than or equal to 1 is less than or equal to expectation of x by 1 by Markov inequality, as we have seen. So, this will immediately tell us that this will immediately tell us that, so if e of x is tending to 0, then this probability that x greater than or equal to 1 will also tend to 0, because this is even less than that as n tends to infinity. So, that is one way of showing that. So, if you take a certain g and p, maybe if p by t is less than it tends to 0 as n tends to 0, this is one way you can try to show. You just try that, then expectation of x also will tend to 0, right. Then immediately, but on the other hand, can we use the same technique to show that the probability of x equal to 0 tend to 0? That means when you want to show that this probability is high, that means it's approaching 1. We may want to show that probability of x equal to 0 tends to 0. But if you simply show, we should take the expectation and show that it has some lower bound with very high probability, that won't be enough, because it is possible that some random values, this random variable may take some very high values for certain things, and then almost all the time it may be 0, but when it is taking some other values, it may be taking very high values. So, therefore, that may be the reason why the expectation is has a lower bound, because expectation is summing over all possible values and multiplying with the probabilities. So, that is not enough that way. So, that is what. So, we need some other technique to do this thing. For that purpose, we need some tools from some more information from the probability theory. So, to show this thing. So, to repeat what we have told now is that when we want to consider this case, the probability of x greater than equal to 1 tends to 0 if p is such that p by t tends to 0, that means p is below threshold. Then the technique, one technique, if at all it works, it can be to make use of the Markov inequality, because this is less than equal to expectation of x by 1, that is expectation of x. And you try, because this is here expectation of x gives an upper bound for this thing, you try to prove that if this happens, this will tend to 0, then this will tend to 0, right. So, and on the other hand, we will have to prove, if it t is a threshold, we will have to prove that when p of p by t tends to 1, the probability that x greater than or equal to 1 tends to 1. That means probability that x equal to 0 tends to 0. Here as we told, expectation will not work, because just showing that expectation is high will not work. So, this needs more ideas. So, what we are going to do is to use something called the variance. So, let us define the variance sigma square of x. Sigma square is equal to expectation of x minus mu whole square. So, in some sense you have this expectation for random values, each value you are minusing the mu. So, you will get a different random variable x minus mu there, and you are squaring these things and then taking the expectation again. That is this thing. It is a quadratic measure of how much the random variable x deviates from its mean. So, another thing, so very easily you can derive that sigma square is equal to expectation of x square minus mu square. How do you do that? So, this is easy, because expectation of sigma square is essentially expectation of x minus mu whole square. So, you can expand it. This is x square plus mu square minus 2x mu. So, because of linearity of expectation, this becomes expectation of x square plus expectation of mu square will be mu square, because it is a constant, minus 2 times expectation of x into mu. That means expectation of x square plus mu square minus 2 mu square, that is expectation of x square minus mu square. This is what. So, this is an easy thing. So, this will be useful in calculations. And now, another thing regarding expectation, the variance sigma is another inequality which becomes very useful, is the Chebyshev inequality. So, say this deviation, the absolute value of the deviation x minus mu going greater than or equal to, that means it is deviating too much from the mean, right, is being greater than or equal to lambda is less than or equal to sigma square by lambda square. The proof of this thing is also like Markov inequality. This is very easy, because because if you want to look at the probability of x minus mu absolute value being greater than lambda, definitely you can see that this is equal to, so if you just square it, so this is this, right. Now, this is less than the expectation of x minus mu whole square, this being considering this as a different random variable, say y. So, this is expectation of y divided by this quantity a, lambda square, right. But this is what? This is essentially sigma square. So, we get this and it's sigma square by lambda square. So, this is immediately following from the Markov inequality, just substituting. So, we are just considering the new random variable instead of x, we are just taking x minus mu whole square. So, this becomes lambda square, and because the expectation of x minus mu whole square is sigma square, this will come. Anyway, so this is all tools from the probability theory, and then now here this statement, this small lemma from Erdos and Renier helps us to do the trick. So, we want to, when we want to say that, see the probability that x being 0 is indeed tends to 0, right. What essentially we want to say, because whenever the graph has x equal to 0, when the random variable takes value 0, it means that its difference, absolute difference from its mean, absolute value of the difference from its mean is equal to mu, because it is 0, 0 minus mu, its absolute value is mu only. So, the probability that x equal to 0 is definitely less than equal to probability that absolute value of x minus mu is greater than equal to mu. Again you can use the Markov inequality here once again. So, that will be sigma square by mu square. If this tends to, this second part, sigma square by mu square tends to 0, Sn tends to 0, then this will also tend to 0, and then therefore, a probability x equal to 0 also will tend to 0, right. So, instead of directly attacking probability of x equal to 0, we notice that this x equal to 0 correspond to x minus mu absolute value equal to mu. So, this probability should be definitely at most absolute value of x minus mu greater than equal to mu. So, this in the Chebyshev inequality. So, we in the Chebyshev inequality in the Chebyshev inequality we have to take the take lambda for mu here, instead of lambda we have to put mu. So, sigma square by mu square, that will that is why sigma square lambda square, instead of lambda we are putting mu here. So, that is why. So, now the good thing about this inequality is that we just have to check, to prove this, the probability that x equal to 0 tend to 0, we just have to verify whether this is tending to 0. So, for our case where the random variables are greater than equal to 0 anyway. So, this is we just have to verify sigma square by mu square, whether sigma square by mu square will tend to 0 or not. So, this is the technique. So, this is the second moment method. So, we will illustrate it with one example, namely the next one will next example will. So, this is, let us again consider the property of so where H is a fixed graph, the PH be the property of containing a copy of H as a subgraph. That means, randomly drawn graph, what is the probability that H is contained as a subgraph. That is the property we are interested in. H should be present as a subgraph in G. So, and we can take a special kind of H. H is called balanced if this epsilon of H dash is less than equal to epsilon of H for all subgraphs H dash of H. What is this epsilon of H? When I say epsilon of H, that is the number of edges in H, E of H cardinality divided by the number of vertices in it, n, right. The number of edges divided by the number of vertices in it, H. This is epsilon. Suppose if you take any subgraph of H, if it so happens that every subgraph has this epsilon value lesser or equal, that means it's a kind of, this will be lesser or equal to epsilon H. In that case, we will say that it is a balance. In some sense, it says that they are now very concentrated portions inside the graph, right. So, the biggest graph captures the maximum edge density, right. So, all smaller graphs will have at most edge density will be at most as much as the bigger graph. This is the property of being balanced, right. Now, let us say the property of being balanced, and now see, to understand what is this balance, why we are considering balanced graphs. That is because many of the simple graphs are balanced. For instance, you can think of a cycle. So, if you consider a cycle, so how many simple cycle on k length cycle Ck. So, there are k edges, and then there are any subgraph if you consider. So, the epsilon will be k by k 1, any subgraph if you take, it will be maximum a path or a collection of paths. So, therefore, definitely the epsilon the edge density is smaller, because the edges are less than the number of vertices there, right. So, therefore, that is some example. So, then we can see that it is not very surprising that this balanced graphs is considered, because many graphs are already captured by that. Now, we will prove a theorem that if H is a balanced graph with k vertices and L greater than or equal to 1 edges, if there are L edges and k vertices in it, then the threshold function for it is n to the power minus k by L. This is what we will prove. For instance, if it is a cycle, then it will become n to the power 1 by 1, sorry, k by k, that is n to the power minus 1. If it is a small tree on k vertices, there are k edges and k vertices and k minus 1 edges. So, n to the power k by k minus 1 will be a threshold function for the property of this thing. So, similarly, if you consider a complete graph, what will happen? There are k vertices, kk, right, k vertices, and k choose 2, k into k minus 1 by 2 edges. This is by after cancelling, this is 2 by k minus 1, right. So, we can put it as threshold function as T of n is equal to n to the power 2 by k minus 1 is. So, we will prove this thing as. So, we told 2-3 examples to illustrate that this is a useful theorem, because many of these cases, in simple cases like trees, cycles, complete graphs, all are balanced graphs. So, therefore, when they are coming as a fixed graph, then we get the threshold functions easily using plugging in this formula, because k and l can be evaluated and substitute, right. So, this general statement we will prove tomorrow in the next class. So, that is, thank you.